All right, here we go. Note 6.1, day 2. And I'm actually going to pull a couple problems from the textbook. So if you want to open a tab on the computer or if you have a book, go to page 495. We're going to start by looking at problem 62. Okay, so 62 and 64 we're also going to do. So let's look at the directions for these problems. It says perform the addition or subtraction and use the fundamental identities to simplify. So we're going to add or subtract, and then we're going to simplify. So you're going to need your formula sheet handy because we're going to be referencing quite a few of those formulas that we have, those properties and identities. Okay, here's problem 62. It asks us to add. Well, what I'm seeing are two terms that need to be added together. I could get a common denominator. That's an option. I have a couple of different options, and we're actually going to do this problem two different ways. Of course, we should end up with the same answer. I'm not sure one way is easier than the other, but I just want you to know in this lesson that for these problems, there are so many different ways to begin these problems, but at the end, no matter what approach we take, if we've done everything else correctly, we should end up with the same answer. All right, I got to add these two terms together. All right, well, this first strategy, what I'm going to do is I'm actually going to just focus on this fraction right here. What I'm going to do is I'm going to look at the denominator, and I'm going to multiply this fraction only, not tangent, by the conjugate of this denominator. Now, the conjugate is going to be this denominator with a subtraction instead of an addition. So I want to multiply by the conjugate of this denominator, and you'll see the big picture of y in a minute. So let's go ahead and rewrite that up here as well. So I'm going to work down. I'm going to bring tangent of x down. I'm going to come over here and focus my attention on multiplying these two fractions together. In the denominator, if you FOIL a sum and difference of like terms, these conjugates, you're going to end up, when you FOIL, getting some canceling, but you're going to end up with 1 minus sine squared x. Now, in the numerator, I could distribute the cosine in, but I'm going to hold off on that for a minute. I'm just going to write down cosine of x, and it has to be multiplied by the quantity 1 minus sine x. Working down again, I'm focusing my attention over here on this term. I saw that if I created 1 minus sine squared x here, I could convert that to cosine squared x, because that's a Pythagorean property, just rearranged. So 1 minus sine squared x equals cosine squared x. I did not distribute the cosine in, so I'll just bring that down because I'm thinking ahead. Thinking, you know what? The numerator's factored. I can divide out this cosine with one of these here. Then I'm thinking, well, I still have a fraction here, but it looks a little bit better. Now I'm going to come over here and change tangent to sine x over cosine x. And I'll clean this up. Parentheses are no longer needed. Notice that we have a common denominator. So let's put these two together. I'm going to come up here. I'm still on the screen. Yep. So I'm going to rewrite as a single fraction with the denominator of cosine of x, and then I'm going to add these two numerators together. All right, I can go further. I see that these two terms will cancel, and I'll be left with 1 on top and cosine x in the bottom. Remember, the directions were to perform the addition and simplify. Well, we don't really want our answer to be a fraction, so the reciprocal properties allow us to say that 1 over cosine x is equal to secant x. All right, let's do this same problem, but let's just take a different approach. Okay, so here's the original problem. Okay, let's take a different approach. What if we decided we wanted a common denominator from the very beginning? Meaning I would make tangent a fraction. Then I would come over here and multiply this term by the same denominator, 1 plus sine x over 1 plus sine x. Okay, and then I'm going to go ahead and I might, when I multiply these two numerators together here, put the tangent x up front. It's going to be over 1 plus sine x. And then let's write this second term down. Oops. Okay, I'm going to rewrite as a single fraction. I might go ahead and distribute the tangent in, unlike I did in the previous strategy, because I don't see anything that's going to cancel. So multiplying in, I get tangent x plus the product tangent x sine x. And then I need to extend here, and then I have a plus cosine x. So I distributed, and then I collected. Okay, at this point, there's so many things you can do as well, but I'm looking at this going, nothing cancels, nothing cleans up. So for me, sometimes it's easy when I'm doing this kind of problem to change anything that's not sine and cosine to sine and cosine. Sometimes that makes it easier, sometimes not, but I don't always know. So I'm going to try that strategy. I'm actually going to skip a couple steps. The denominator's good. Paying attention to tangent, it becomes sine x over cosine x. Plus, now I'm here. I'm going to change tangent to sine x over cosine x. That's just tangent, but I still have to multiply it by sine x, so I might as well make sine x a fraction. And then I just have cosine x over here. If you wanted to make it a fraction, just put it over 1. Looks like it's just more messy than what it was before. Okay, let's see what we can do. We'll kind of clean it up a little bit. I see I need to multiply these two together, which results in multiplying the two numerators, sine squared x over cosine x, plus, now over here I'm noticing that I need a cosine x in the denominator if I want a same denominator in the numerator of this big fraction. So what I might do is when I notice that, go, well, let me get this to have a denominator of cosine x here, and put cosine x here. So then I'm going to have cosine x here, and then cosine squared x in the top. And remember, this is still all over 1 plus sine x. Whew, okay, so here we go again. What I'm going to do is I'm going to bring 1 plus sine x underneath the fraction bar, the big fraction bar. I'm going to focus my attention on what's going on up here. I'm going to rewrite the numerator just so that it has a denominator of cosine x. So I've got sine x plus these two. Still looks pretty complicated, but let's look at what's going on here. That's actually just equal to 1 because of a Pythagorean property. So I'm going to come back up here and I'm going to write sine x plus 1 over the cosine. And then don't forget, we still have 1 plus sine x in the denominator. But hopefully you see that sine x plus 1 is the same as 1 plus sine x. So if you wanted to make the denominator of this bigger fraction another fraction, and we're going to actually keep change flip, multiply by the reciprocal. So let's keep the numerator, just this numerator, times the reciprocal of the denominator. So now I'm back to multiplying, but hopefully you can see that sine x plus 1 will divide out with sine x plus 1 here. We're left with 1 over cosine x. which that will convert to secant x. Same answer we got by using a different approach. Oh, goodness, goodness, goodness. Hopefully you see all that. Sorry about not pushing that up there. Oops. I'll leave this up here for a second, or you can pause and kind of copy it down. Maybe go back and listen as you look back at your work that you have there. Okay. So we ended up with the same answer. I think the first strategy probably was the easier one, but how would I know that on the front end? I don't know it. Honestly, I just jump in and start working it out. And the first time I worked this particular problem, I worked it this longer way, and then I thought, well, gosh, there's got to be an easier way. So I thought about conjugates and just working with one fraction here instead of trying to get a common denominator. So it doesn't matter. We all end up with the same answer. Okay. All right, we're going to look at problem 64. Same thing. There may be multiple strategies, approaches. I'm going to take a moment and look at this and think about what I might do, kind of plan. Yeah, I could change to sines and cosines. I could change tangent to sine x over cosine x. I could change secant x to 1 over cosine x. Probably the reason I wouldn't change to sines and cosines is because of what's happening here. I don't want a denominator with 1 plus 1 over cosine x. I guess I could get it. I guess I could get a common denominator in the denominator and kind of clean it up. There are so many ways to enter into this problem. It doesn't matter. All right, let me think about what strategy I might use here. Should I get a common denominator? Probably. Let's see. I'm thinking I might actually change to sines and cosines on this one. This is a new approach for me. Let's see. My original approach that I was going to do with you is to multiply this fraction by tangent x over tangent x, and then multiply this fraction by 1 plus secant x over 1 plus secant x. And that'd be fine. I'll tell you in advance, this is the answer we're trying to get. 2 cosecant x. So we know if, no matter what strategy we use, we get this answer, we did it right. Yeah, I'm seeing a new strategy. I'm going to take this fraction and change everything to sines and cosines. So I might skip a couple of lines here. So tangent is going to be rewritten as sine x over cosine x. Down here, got the 1, it's good, but secant's going to change to 1 over cosine x. Over here, the numerator. Oh, let me fix this. The numerator is going to be 1 plus 1 over cosine x, and the denominator is going to be sine x over cosine x. Wouldn't it be nice if we could divide these out across this way and across this way, but we can only divide out if we're multiplying. I've never done it this way before. I hope I haven't just made it more complicated. Okay, so what I'm going to do is I'm going to focus on getting a common denominator here and here. So I'm going to keep sine x over cosine x on top. And then here, I'm going to multiply this 1 by cosine x over cosine x. Which means down here, I'm going to have a denominator of cosine x. And in the numerator, I'm going to have cosine x plus 1. Same thing over here. If I multiply by cosine x over cosine x, I'm going to get cosine x plus 1 over cosine x. And then I'm still going to have sine x over cosine x here. Yeah, I'm starting to regret this strategy. Okay. I think I'm going to now work on keep change flip here and keep change flip here. So bringing down this numerator, sine x over cosine x, I'd end up multiplying it by the reciprocal of this fraction. So cosine x would be on top, and cosine x plus 1 would be on the bottom. I'm going to come over here and do the same thing. keep, change, flip. I'm going to keep the numerator. And multiply it by this reciprocal. So working on this term right here, I see I can divide out the cosines. And over here, when I multiply, I can divide out the cosines. I don't think this helped me. So I'm going to have sine x over cosine x plus 1 plus cosine x plus 1 over sine x. Yeah, my other strategy wasn't any better. I'm going to get a common denominator. I'm going to multiply this fraction by sin x over sine x. And I'm going to multiply this fraction by cosine x plus 1 over itself. Okay, I'm going to come back up here. So, let's see. Multiplying these two fractions together, I'll have sine squared x on top. I might leave these two factored, so let's see. Sine squared x over sine x times parentheses cosine x plus 1 plus, I'll leave these two denominators, or this in factored form. Oh my goodness. And then I'm going to multiply these two together. Wow. By foiling. I'm second guessing this strategy, but you guys can see what I go through too. All right, same denominator. The numerator, once foiled, is cosine squared x plus 2 cosine x's plus 1 when you foil. Rewrite as a single fraction. I'm going to add all this. I'm not going to multiply sine x in just yet. I'm going to see if I can clean this up and maybe divide something out. We know these two are going to be equivalent to 1. Let's replace that with 1. So I've got a 1 here plus this 1 here. So in the numerator, I still have 2 cosine x's plus now 2. One of these came from here and the other one came from that property. Let's take the numerator and factor out a 2. These divide out, I'm left with 2 over sine x. You could write 2 divided by sine x as 2 times 1 over sine x. And then this is going to become 2 times, and then this can be changed to cosecant x, which is what I had mentioned the answer was. I've done this problem 2 or 3 different ways. I would say maybe, I don't know if this is the most difficult, but it certainly wasn't the most easy. Okay. All right. All right, let's move on. We're going to look at a couple of different problems in this section as well. And I'm going to show you the directions for those problems. We're now going to do 68 and 70. So 68 and 70 are down here. Notice we have just a single fraction in each problem, but the directions say rewrite this expression so that it is not in fractional form. So we've got to get rid of the fraction. Good news is these are a little bit easier. All right, let's take a look at 68. So tangent squared x divided by cosecant x plus 1. We don't want a fraction. For these two problems, when you're not adding or anything or subtracting fractions, but you don't want a fractional answer, okay, I would say that to enter into these problems, it might be best to multiply this by the conjugate of the denominator. Remember, the conjugates just change the operation. All right, now in the denominator, I'm going to multiply these two together. And when I FOIL, I'm going to have some canceling, and I end up with cosecant squared x minus 1. I'm not sure yet if I want to distribute the numerator, tangent squared x, into cosecant x minus 1 yet. I'm not sure. I might later, but we'll just wait and see. All right, so what should I do next? Well, I don't want to factor the denominator because it's going to get me back up here. I want you to think about your Pythagorean properties. Okay, hopefully you can see this. 1 plus cotangent squared x equals cosecant squared x. So what I'm going to end up doing is I'm going to end up thinking about rearranging this. If I were to subtract the 1 to the other side, I know that cotangent squared x is equal to cosecant squared x minus 1, my denominator. That might help me. So I'm going to replace this denominator right here with cotangent squared x. So we multiplied by the conjugate, didn't distribute in the numerator. Oops. I end up here. Okay. What I want you to see is that this denominator right here, cotangent squared x, could be made to a fraction to put it over 1, and I could keep, change, flip. Or if you want to think about, you know, well, yeah, keep, change, flip, I guess, is what I want to think about. So I'm going to leave the numerator. And I'm going to multiply this by, when I keep, change, flip, well, that's going to still give me what? 1 over cotangent squared? Well, that's fine. I'm just not seeing where this is going yet. So I'm multiplying. Oh, there it is. I see it now. Maybe you did too. I'm going to change this. I'm going to change that to tangent squared x because I have a property that says that that's equal to tangent squared x. Now what I'm going to do is I'm going to think about, these are just things being multiplied, so let me multiply the two tangent terms together and get tangent to the 4th x times cosecant x minus 1. There it is. As ugly as it is, that's my answer because I don't have a fraction. That's what just happened right there. Let's try another one. I go to problem 70. This is what 70 looks like. So our objective, no fractions as an answer. So for this kind of problem where you're not adding or subtracting, I said you might want to multiply by the conjugate. So this conjugate is tangent x minus secant x. All right, next line down. I just put the 5 up front of a parenthesis. I'm not distributing that 5 in. I don't see there's any benefit. Now let's FOIL these two. When we FOIL, you're going to have some canceling, and you end up with tangent squared x minus secant squared x. If you're not sure where this is coming from, I just suggest going over here, you know, and multiplying it out by FOILing. Oh, well, look at these two terms down here having both with an exponent of 2. I know there's a relationship between tangent squared and secant squared with one of the Pythagorean properties. So I know 1 plus tangent squared x equals secant squared x. Wonder if that'll help me. Well, sure. I guess I can replace secant squared x with 1 plus tangent squared x. Ooh, that would be good. Keep the numerator. Where secant squared x is, I'm going to replace it with 1 plus tangent squared x. So I got tangent squared x up front minus, don't forget to use parentheses. Remember our goal, we don't want a fractional answer. So let's distribute the negative. Minus 1 minus tangent squared x. Well, that's convenient because these two are going to cancel. So I have it 5 times quantity tangent x minus secant x all over negative 1. Again, remember, we don't want a fraction, so how about we just bring the negative up front with the 5 and ditch the fraction. That's it. All right, so you might want to look back and think about why we did what we did for each of these different problems, but your properties, your formula sheets are pretty important here, okay? One last objective. On your assignment, you're going to be asked to answer these questions, 111 to 114. So I wanted to make certain that you knew different strategies to answer those questions. Here are my 3 made-up examples that go along with these problems. As x approaches, not equals, that's what the arrow stands for. We're beginning to look at calculus ideas. As x approaches the value of pi over 2 from the right, notice that superscript is a positive. We interpret that as x has to approach pi over 2 from the right. Then what does cosine of x have to approach? And this is our blank here we're filling in. And if this is also true, what does the secant of x have to approach? So where these 2 blanks are, we want to fill those in. So I'm going to write down 2 more problems here. Once we get these recorded, then we'll go back and tackle the answers. So as x approaches 0 from the right, if I wanted to approach 0 from the left, it'd be a little minus sign up here. Sine of x is approaching what number? And cosecant, its reciprocal of x, is also approaching what number? In our third example. Now I'm going to skip an extra line here. As x approaches pi from the right, I'm not sure why I didn't choose any from the left with the negative. Cotangent of x approaches what? And tangent of x, its reciprocal, approaches what? These probably seem pretty weird because they are limit statements basically from calculus, but let me see if I can go back to this first example we wrote down. It says, as the x coordinates approach pi over 2 from the right on the cosine graph, what are the y coordinates approaching? Well, I think a graph of cosine x is going to help us understand this. So what I'm going to do is real quickly draw underneath here a little cosine graph. Cosine starts up here at 0, 1, you might remember, comes down like this, and it concludes over here at 2 pi. So let's find pi over 2 because we want the x coordinates on this cosine graph to approach pi over 2. We might remember this is pi and this is actually pi over 2. If this is pi over 2, I know this ordered pair is exactly pi over 2, comma 0. This notation says, go to where x is pi over 2, but put yourself to the right of pi over 2, like right here. Now find the graph. It's right here below you. Now take yourself and move yourself so that as you move along this graph, either up or down, your x coordinates are getting closer to pi over 2. So what are the answers approaching? Well, the y values are approaching the y value right here at pi over 2, which is 0. Okay, likewise, on the secant graph, which I'm not going to draw, because secant is just the reciprocal of cosine, what would the secant values be approaching as x goes to pi over 2? Well, the answer to secant is actually just going to be the reciprocal of 0. You might remember that you can take 0 and put it over any number. I'll just go ahead and put it over 1. Reciprocate this fraction. Well, secant approaches 1 over 0. Well, 1 over 0 is a vertical asymptote. So our answer for this problem is undefined. There must be a vertical asymptote on the secant graph at x equals pi over 2. If you look back at your secant graphs on your formula sheet, you'd probably see that. All right, so let's look at this problem. What do the y values, the sine values, approach as x approaches 0? Let's find this answer first and then find its reciprocal. So let's draw the sine graph. Sine starts at 0, goes up and then back down, and here's 2 pi. It also extends back this way. Okay, so the problem asks us, as the x coordinates on this sine graph, because we're working with sine, approach 0. Well, here's x equals 0. From the right means let's just move a little bit to the right of x equals 0, put ourselves on the graph. But instead of moving up where x coordinates are moving away from 0, let's move down. What are the y values approaching? The suggestion is that I'm going to 0. So instead of drawing the cosecant graph, what's the reciprocal of 0? What's undefined? If we were to draw the cosecant graph, we would probably see a vertical asymptote at x equals 0. Look back at your graph and that should confirm it. All right, third and final example. I'm not going to work with cotangent. I could, but I'm going to instead work with tangent. As x coordinates approach pi from the right, what are the tangent values going to be? And then I'll reciprocate this answer and record it here. Well, you might want to look up your tangent graph. We have vertical asymptotes at pi over 2 and negative pi over 2. Okay, but I'm approaching pi, so pi must be about right here because this is 3 pi over 2. Well, here's pi. And tangent goes something like this. So as x approaches pi, here's pi, x equals pi from the right. Okay, so I'm putting myself to the right of pi, jump up, find the graph. But you want to move down because x coordinates are getting closer to pi. If you go down, what are the y values approaching? 0. The reciprocal of 0 is undefined. Just real quickly, if I were to draw the tangent graph, it has vertical asymptotes at 0 and pi. And the graph goes something like this. So if I had drawn cotangent instead of tangent, as I approach pi from the right, well, pi's at an asymptote. From the right of pi means I need to be looking at this other part of the graph. As I approach pi from the right, here's pi, jump to the right, jump on the graph, but move upward so your x coordinates get closer to pi. Notice that I'm approaching an undefined situation. So we could have looked at it from either on here. Doesn't matter, I just chose the easiest trig function to sketch a graph of to interpret what's going on here. I hope this helps.